So in 8.3b, we're going to determine the critical value for calculating the confidence interval for the means and determine the critical value that impacts that confidence interval. But keep in mind, because we're analyzing data or statistics about a population, is because we don't know about the population. So in these cases, that sigma sub x, we don't know it. So because of that, we can't use z anymore. We are now going to start focusing on t. Let me show you how to do this. In this example, suppose you want to construct a 90% confidence interval for the mean of a normal population based on an SRS of size 10. What critical value t star should we use? Now, it does say it's a normal population. Remember, the t looked like the z distribution, so it's approximately normal. It's just that we don't know the standard deviation of the population. So to do this, it works exactly like you did for the z critical value. In that case, we use table A. But for the t critical value, we now move on to what's called table B. So let me show you how this works. Since they want a 90% confidence interval, let me just give you a quick sketch of that, right? So we have this. Remember, this is our mean of 0. At 90% confidence, that's 90% of our curve. Well, 10% of the graph's not being used, but remember, it's equally distributed between these two tails, which means each of these two tails is 5%. Now, here's how this table works. If you go to table B, it's in the back of your note packet. This is up down here on the rows are listing the degrees of freedom. So they're going to say, what degrees of freedom are you looking at? Well, you have to remember how to calculate degrees of freedom. Degrees of freedom, we abbreviate with DOF. It's just n minus 1. So sample size is 10 minus 1. So we're going to look for the 9 degrees of freedom, which is right here. Now, what do we look up here for which column? You look at what's on the upper part of the tail of your curve. So for this is our actual picture of our confidence interval. The upper tail is actually right there. So what percent is that upper tail? It's 5%. Therefore, I would go over to the 5%, which is right here, and then I just see where it actually comes together. This is actually how many standard deviations I am from the mean. And from that, we can now record that the t critical value, therefore, is 1.833. Now, that's how you use the table. The calculator is actually quite easy for this. It works just like inverse norm, but you don't use inverse norm. You go to the calculator and you're going to look for inverse t. Now remember, you're going to find that by hitting second vars or second distribution. Now, this, remember how inverse norm works, it's actually going to look at the area to the left on this one. So it's actually backwards from what we do on the table. And then we're going to type in the degrees of freedom. So on here, the area to the left, this is the one we want. The area to the left is 95%. So what I would type for here is I'd put 0.95. My degrees of freedom in this case is 9. If you do that, you will end up getting this value on your calculator. So in finding the t critical value, again, be cautious, they're backwards. If you use the table, read what the table says because it shows you in their actual directions above. This is the area to the right within the tail, but the calculator actually works area to the left just like inverse norm. In 8.3 E and C, let's calculate and interpret the standard error of the means, and then construct and interpret a confidence interval by checking all of our various parameters that we need and interpreting the results in context. Now, the definition of standard error of the mean is for x bar, and it is just what we've been talking about. It is s of x over the square root of n. And it's where s of x, the sample standard deviation, it describes how far x bar will be from mu on average and repeated SRSs of size n. Okay, how do you construct the confidence interval? Well, notice the standard error of the mean is actually here in the confidence interval as we would expect. All the confidence interval is this. In terms of the words, it is a one sample t interval for a population mean. How do you find it? Just like we've been doing before. Take the point estimate. The point estimate for the mean is x bar. We're We're going to do plus or minus the t critical value, that is how many standard deviations we are from the mean, and then we're going to times it by the new standard error and just use this particular formula. Now again, before we do this, we always have to check our conditions, which are going to be random, normalcy, and for independence. The random is how it's always been. The independence is actually going to be stated right here. The population is at least 10 times as large as the sample. That's the 10% condition we've been talking about. The only difference now is for normalcy. When you check normalcy for this, we're going to use the central limit theorem basically, which said to assume approximately normal, our sample size has to be greater than or equal to 30, which we've already talked about. This formula you will find is on the formula sheet. So let me formally talk about those conditions again. The random check, again, is easy. We're just going to look that the data is from a random sample of size n from the population, or if it's from a randomized experiment. So if they're doing a survey, we're going to see it's a random sample. Or if it's done in an experiment, you don't necessarily need a certain sample size. It just has to be a randomized experiment. Okay, for the, let's go to independence because we've just talked about that. When you're sampling without replacement, remember, from a finite population, you must check that 10% condition. Again, it just says our population is greater or equal to 10 times our sample size. Keep in mind this independence rule really comes around because of the fact that we are sampling without replacement. If we are replacing it and putting it back in there, then you actually would never do the 10% condition. If you replace it and put it back in, then independence is actually created, and that's all you have to say is clearly they're independent. So start keeping in mind, don't overstate the 10% condition if replacement's going on. It's only when there is without replacement. Then the third condition is the normalcy. There's a couple different ways. For normalcy, if the population has a normal distribution, then we already know that this sample will, so we say it's approximately normal. Or if the sample size is large, that is if the sample size is greater than or equal to 30, then we know our sample is approximately normal. Now, the new thing is this, because of the t-distribution, if n is less than 30, you have to actually go ahead and graph the distribution and look for skewness and outliers to actually decide what to do in this case. You can decide what your graph should be, a box plot or a dot plot, something like that. But be cautious if it is less than 30. If you do not have a graph shown and you talk about this, don't talk about the skewness and outliers of the graph, you will not get credit for this condition. So I am going to encourage you to actually remember to look at the handout I gave you of all the different test and confidence interval procedures that have the conditions listed that you must check, the calculator, keystrokes, and the actual formulas themselves. This one is on here, a one sample mean, if the population standard deviation is actually unknown. So let's look at an example on how to do it in terms of state, plan, do, and conclude. So here, as a part of their final project in AP Stats, Christina and Rachel randomly select 18 rolls of generic brand toilet paper to measure how well this brand could absorb water. To do this, they poured 1/4 of a cup of water onto the hard surface and counted how many squares it took to completely absorb the water. Here are the results from their 18 rolls. So these are how many squares, again, it took them to absorb that 1/4 cup when they did it 18 times. They want us to construct and interpret a 99% confidence interval for the mu, which is the mean number of squares of generic toilet paper to absorb 1/4 of water. So the state in this condition, what are the parameters and confidence level? So for state, we're going to say we want to estimate mu, which is the mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water and with 99% confidence. Okay, what's our plan? Now, for the plan, again, refer back to the handy sheet I gave you of all the confidence intervals and tests. What method or confidence interval are we going to do? All you need to state here is that we're going to do the one sample t interval for the population mean, and we'll get credit. Okay, let's check our conditions. For randomness, this we would say here, students selected the rolls of generic toilet paper at random. And then for the independence, we can actually say here that Students are sampling without replacement, so we're going to check the 10% condition. It's reasonable to believe that there are more than 180 rolls of toilet paper. Now, normalcy. Here we have to be careful for the normal condition. Our sample size here is 18, so we cannot use the fact of the central limit theorem. We also do not know if these rolls of toilet paper are coming from a normal distribution. So you are required in this case to actually graph out the distribution of these results. So you're going to show a graph. I chose to look at a dot plot. So this is a dot plot of the 18 observations from our experiment. Look at this and talk about the skewness and the outliers. And here's what I'm going to say. We would say, since the sample size is small and you don't know if the population is normally distributed, you must check if it's reasonable to believe the population is normally distributed. So in the dot plot, there are no outliers or strong skewness. So it's reasonable to assume it's approximately normal. This is exactly how you have to address the situation to show approximate normalcy in this case. Keeping in mind, this is only required if we are doing for the means or the t-critical value. And in this case, we have to start switching over to this t-interval because we do not know the population standard deviation. Rarely will you even use the z-test anymore going forward on the means. On the do portion, we're going to take that data. I'm going to do in my calculator, I can compute list 1. If I put list 1 in there, what I could do is one variable stats, get the mean number of squares and the standard deviation. By the way, right here, let's don't forget to talk about the degrees of freedom. So I'm going to continue on to here, and for this, say that we have 17 degrees of freedom, and we want a 99% confidence. So 99% confidence, we're going to actually have to find that. How do we do it? Well, in this case, let me just sketch it out. Remember, 99% confidence on here is going to give us this entire region. But we want to know from here all the way down. Well, if this is 99%, it means we have 0.5% in each tail. So the total area we're looking for is 0.995. So I'm going to do an inverse t of 0.995 and put my degrees of freedom in there. Once I do that, I'm going to get that the critical value is 2.898, which means that's on average how many standard deviations I am from this mean. Okay, what if I wanted to show calculating the confidence interval by hand then? I could do this, and here, as I scroll down, is the formula for the confidence interval. I'm going to plug in the value of x bar. I'm going to do the critical value right here we see, and then we're going to actually bring in the standard error here. If we simplify this calculation, what we're going to end up seeing for the interval is this right here, and this will be our confidence interval that we've come up with. Now I do want to actually show you how to do this on the calculator, because as long as you've stated that we're doing the one sample t-interval for the means, if you've said that somewhere, you never have to actually list this. You can use the calculator. The calculator is actually very easy for this. So the keystrokes you're going to want to do is you actually want to click on Stats button, and remember, scroll over to Test. On Stats Test, what you're actually looking for is the word t-interval, and what you're going to see are these screen options right here. So t-interval is number 8. Now when you click on that, you're going to have two options. You can either click Data, and it'll ask you for where what list your data is in, list 1 or list 2, or you can just scroll and hit Stats. I like using the Stats one, and I'm just going to type in the mean there that we got, the standard deviation that we got. Sample size, not degrees of freedom, so make sure you put 18, and then the confidence interval. And then you just click Enter, and then you're going to notice here we get the exact same answer as we had gotten here before. So I can state this right here instead of having to show all of this work. Now, if you use the calculator, and ultimately I recommend that you do, it's easy and it's slick, you do have to state the degrees of freedom. So I'm going to do a DOF as a shortcut. They're fine with that. Remember, your degrees of freedom was 17. So if you state that for calculator speak, we have degrees of freedom. Make sure we've stated the mean and standard deviation somewhere so that gets covered. So really you could just write all of this down on the screen, write the confidence interval, and just add the degrees of freedom, and you should be fine. Now, there's one thing the AP Board will highlight to you, and this is actually not in this example, but it says here, be careful. If the desired degrees of freedom is not in the table or table B, you need to find the next smaller degrees of freedom that we're looking for. If I use the calculator, the table is completely irrelevant, and I do not have to worry about making this mistake. But if you were to go to the table, and you're going to use table B and find this critical value of 2.898. If you don't see the degrees of freedom, because they don't list all of the degrees of freedom, they're going to say round to the next smaller degrees of freedom. And we're going to see this come up and happen in our last example. Okay, let's wrap up with our conclusion for this. Don't forget how to do it. We are 99% confident that the interval from 22.99 squares to 26.89 squares captures the true number of squares of generic toilet paper needed to absorb a quarter cup of water. Just look at one more example and call this done. How much homework example? The principal at a large high school claims that students spend at least 10 hours per week doing homework on average. So 10 hours per week on average, that's a means, so it's quantitative, by the way. To investigate the claim, an AP Stats class selected a random sample of 250 students from their school and asked them how long they spent doing homework during the last week. The sample mean was 10.2 hours and the standard deviation was 4.2 hours. Construct and interpret a 95% confidence interval about their homework. So let's state the situation. What I want to do here is we want to estimate mu, which is the mean time spent doing homework in the last weeks for students at this high school with 95% confidence. Okay, let's go into the plan. So the plan portion for this, we will construct a one sample t interval, provided the conditions are met. And remember, it's nice to state the one sample t interval right up front here so we don't have to show the formulas. So let's just look at the conditions. So for randomness, on this one, if we take a look at it, is it met? Yes, we selected a random sample of 250, so I can see it right up there. How about for normalcy? So for the normal condition on here, the sample size is actually 250. So because of that, we can say it's approximately normal, and we're safe in using the T procedures. And then the last one is for independence. Now, we are sampling without replacement, so we must show the 10% condition. In this case, I'm going to take 10 times 250. I can assume that our population is at least greater than 2,500. Okay, let's do the due portion. So for the due portion on this, here's what we're going to do. We have our degrees of freedom. We do want to state that. It's going to be 249 degrees of freedom. And again, we want to construct a 95% confidence interval. Now, if I use the T table, which is table B in this case, you are actually not going to find 249 degrees of freedom. Remember, for the confidence interval here, if we're talking 95 is in here, if you use the table, it's going to use this tail here, so it's 0.025 if we use that. You want to be conservative in the table because 249 is not there. Go to the next smaller one is 100. So in the table, you would use 100 and then 0.025. If you do that, you're going to get a critical value of 1.98. Okay, fine, let's put that in the formula then. The formula then for the confidence interval, again, this is the standard formula. Keep in mind, if I stated it up here already, I do not have to show this right here. I don't even have to show this if I use the calculator, but let's plug it in. Right, our mean is 10.2. The standard deviation is right there over the square root of the sample size and the critical value. If we simplify, we get this right here for the confidence interval. Now, let's just make an conclusion real quick. We're 95% confident that the interval between 9.67 hours and 10.73 hours captures the true mean number of hours of homework that students at the school did last week. Okay, I want to go back, though, to the due portion. I personally like to use the calculator. Why not? So remember to access the calculator information. It is going to be stat, and you scroll over to test. We're looking for, in that, the t interval. You're going to be asked to actually put in the mean, your standard deviation, and your sample size of 250, not your degrees of freedom. When you hit enter, you're going to get an incredibly close confidence interval. In the calculator, you actually get 9.67 and 10.72. Again, I'm using the calculator because it's way easier and less work. If I do that, though, I have to be incredibly careful. Somewhere in here did I state the mean and standard deviation. For myself, if I didn't, I'm going to have to list down here that the mu of x is 10.2. And then the standard deviation of my sampling distribution is sigma of x. In this case, remember, it's going to be the 4.2 over the square root of my sample size, which is 250. Now, the last thing you have to state is the degrees of freedom. So I'm going to put DOF, remember, is going to be 249. So they are looking for the fact that we have the mean there, we have the standard deviation of this listed, and we have the degrees of freedom. So we would be covered with our calculator speak. Wrapping it up, based on the interval that we computed, can you conclude the principal's claim? Remember, he had said at least 10 hours were done, and our interval was 9.67 to 10.72. Now remember, he wants to know if at least 10 hours were spent, but in this interval, I have something less than 10 hours. So because there's within the actual interval something less than 10 hours, we can't claim it. What we'd have to say is this. Since the interval of plausible values for include values less than 10, the interval does not provide convincing evidence to support the principal's claim that the students spent less than 10 hours on homework per week on average.